Okay, so looking at applying Newton's laws. So we have the person dragging the suitcase. Okay, so you know, I have the normal force, weight of the suitcase. And friction force. And then applied force. Help ourselves out. Know our x and y directions. Know our angle theta. So then we can start looking for our components. Now, of course, she's dragging the suitcase with cord. We don't have to really worry about tension because this applied force vector, you can either call it tension or applied force. We solve for the same thing. Okay, so what's asked? So we know that theta 40 degrees. Mass is 36 kilograms. We're trying to figure out what that applied force is. Okay, so all right, so let's start with the net force in the x direction. So notice we have the x component of the applied force plus the kinetic friction force, and this is a system with no acceleration, meaning that what kind of system is it? What is the net force equal in a system with no acceleration? Zero. Okay, so we look at the directions of our x component and our kinetic friction force. The x component is positive, friction force is negative. We're going to get an x component that equals the friction force. So let's put in some equations for these. What do you want to call the x component? The x component. What does the component look like?
Sine.
Cosine. Yeah, sorry.
Because we want to end up solving for that force F. What about the friction force? What does it look like? U times the normal force. And so in this case, we're going to need that normal force because we're going to end up talking about forces in the y direction. Okay. Now, let's look at forces in the y direction. So, you're going to have The y component of our applied force plus the normal force plus the weight equals 0. We take account of the fact that up is positive x, down is negative, up is positive y, down is negative y. So we're going to end up getting component plus the normal force equals the weight. What can we put in for weight?
Mass times
Mhm.
9.8.
Mass times gravity. We remember what gravity is?
9.8.
Okay, so we'll end up using that. Okay, so let's put in, so if the x component was cosine, the y component has to be sine. We're going to substitute in our equation for the normal force. Equals mass times gravity. You're going to multiply through by the coefficient of kinetic friction. We can factor out the force that we're trying to solve for. And then finally, we end up at the equation. So in the denominator here, we're going to have K sine of theta. We end up there. So this is the point where you can start plugging in numbers. Again, I don't expect perfection, but I want you to try to get here. So what are we going to have? Well, we look at the problem, we see that the coefficient of kinetic friction 0.13, the mass, kilograms, gravity, over 0.13. 40 degrees. It's a cosine of 40 degrees, and now you get some good practice with your calculator, keeping all the numbers straight. And you should end up at about 4 newtons. Remember, use parentheses as much as you have to, because don't ever trust your calculator's order of operations. You still have those calculators that you just hit the button that says solve. Someone had those. One of those last year, just put stuff in and just solve and the calculator would do it.
Oh, the numbers.
Yeah, that one.
Yeah, those are the best.
still have Texas Instruments.
What you see is what you think.
Yeah. All right. So here we're going to be looking at Newton's laws with an object on a slope. The brick of mass 1 kilogram slides down an icy roof inclined 30 degrees. Let's see, if the brick starts from rest, how fast is it moving when it reaches the edge of the roof 0.9 seconds later? The coefficient of kinetic friction is 0.2. Okay, so. So we have our break on the slope. Now, remember the gravitational force is going to point straight down. Normal force is going to point straight out perpendicular to the surface. Okay, so let's see. We have our kinetic friction force. And then, well, let's just go ahead and say that. So my positive in these directions. So then, we know that our gravitational force is going to have components. We know that theta (30°). We have to solve that triangle. Where can I move theta to?
Is it the same as that? Theta that we have for gravity?
Yeah,
Is that
so
the same one? Theta?
we can move it right there.
Why can I do that again?
Well, on the video I gave a, there is an analytical way to do it, but it's going to involve geometry. Another way to think about it is kind of think of that gravitational force vector as a swing arm. Imagine it's just on a pivot. And so if the slope is flat on the ground, that well, let's see here. I don't know if the microphone will pick it up. But anyway, if this is flat on the ground, this arm will swing back into the y direction. Okay. So then for every degree that I rotate that slope up, this gravitational force will swing out like that. So you can think of it as a swing arm on a pivot. So then this could be your entire free body diagram. Sometimes I move the X component so that it reminds me that it's the one that's working with friction. So still, it's the same component. It just sometimes that shows you like, oh yeah, this is when I do the sum of forces in X, this is the one that's going to go with friction. Okay, so we want to know what the final velocity is. Okay, so let's start out by just looking at what we have. So if we look at acceleration, we know we can change acceleration into okay, we know we can do that. Now, let's go ahead and break this down so we have the final, the initial, T. So this is something to start getting used to because you're going to start doing it a lot in the next chapter. And so, and beyond that, when we're using kinematic equations. So based off what the problem says, one of those velocities can be made zero. What is it? Which one is it? The initial one, because the problem says starts at rest. You love problems that say starts at rest because your initial value is a zero. Okay, so no, our delta T, yeah, it's 0.9 seconds. We don't know acceleration, so we need to figure out what that is. Okay. Now, if we start looking at the y direction here, gravitational force in the y direction plus the normal force. This one is zero. Why is some forces in the y direction zero? Right, well, yeah, because you imagine the brick is sitting on there, it's not continuing to fall through. So a normal force in the gravitational force, there's no motion. Yeah, we'll just say there's no motion in the y direction. So it's going to be zero. So we know we set our direction so that normal force will be positive. Gravitational force in the y direction is negative. And then if we go ahead and put this in as our component, but we don't know what the gravitational force is, so we can make one more substitution. Okay, so now we have something we can plug in for our normal force, because if you remember, we're going to end up needing that when we get to friction. You could have started with forces in the x direction, got to a point where you had the coefficient times the normal force, and say, oh, I need to know what the normal force is so I can plug that in. Okay, now, a little bit of a change here. Why is it not zero? Why are we now applying Newton's second law all the way
It's
through?
moving.
Well, not just that it's moving.
It's accelerating.
It's accelerating. It starts at rest. By the time it's traveled for 0.9 seconds, it has a velocity. It's being accelerated. Now, based off how we have x and y set, that's positive. Oh, I already showed you. I'm supposed to put plus there. The kinetic friction is negative. Okay. So let's start plugging things in that we know. So if our component for y was cosine, this one has to be sine. And the kinetic friction force. Okay, so we can then change this to g theta. And then, since we have an equation for the normal force,
Would it be okay if like on your homework, you already like solved out normal force before, so you can just keep N in? Like you already put in the.
yeah, that would actually be fine. I do want you to go ahead and solve for, we're gonna get to an equation for acceleration. No. No, actually, in this case, it wouldn't, because you're gonna see that some of the components of the normal force are going to cancel out. So try to derive all the way through, because you'll see what we're talking about here in a second. Now I can factor out the mass times gravity. If you ever get to a point and you've solved for the variable that you're trying to find, and the n is still in there, then yeah, that's fine. Okay, so then we're going to divide through by m. Then we have an expression for our acceleration.
The M's cancel out.
Yep. So then I can go back to that equation for velocity. Plug in my equation for acceleration. And the delta t will be easy because it's just the 0.9 seconds from the problem. Because again, your delta t final minus t initial, your initial time is where you started timing, so it's 0. Zero.
What did you say our delta T was?
Well, so the delta t is just going to be the 0.9 seconds, because sometimes you'll have to break it down into t final minus t initial, but in this case, your initial time is where you just started taking time.
Okay.
So your t it'd be t final minus 0.
Minus 0.
So it'd be like 0.9 seconds minus 0.
Okay.
Then you end up with about 2.88 meters per second. So now, theoretically, if you were working on this on an assignment, would I like to see you do it just like this? Yes, but I realize this is new, and this looks like a lot of stuff when it's the first time you're doing it. I want you to give it your best effort. If you just give me, so you see how long this derivation is. If I get a problem and I have just like that much and then numbers plugged in, I want to see effort. I don't want to see perfection. I want to see you at least try to do this, in which case you'll be fine. Okay. Now this one is your standard Atwood machine. Most people hate this one, and you'll see why. Okay, so we'll try to make it as painless as possible. No.
try to do a hexagon, 'cause you don't know how
I
to
can't,
do it.
man, I can't. There. Wow.
I hated that class. That class was evil.
A hexagon, really?
And then the squares.
Yeah, so you have a pulley hanging from the ceiling.
She has.
You're gonna have two masses. No,
She just had like 3 days. Yeah, this thing's.
So you have your standard Atwood machine. Acceleration.
Split thousand.
So it's going to be moving around that way. Mass 1, mass 2. And then what is this? Verify Newton's second law for the two blocks. Okay, so what we're going to need is we're going to need the sum of forces in Y equals mass 1 times AY. And so when I do the sum of the forces and I multiply mass times the acceleration, they should come out to both be the same number. So let's look at what sum of forces in Y looks like. Let's see. How's tension going to look? Which one of these? Okay. Okay, so that's our basic free body diagram. So then we can say, well, we'll be working with mass 1, tension, 1G. And to help ourselves, positive Y is going to be up. Okay, so that's going to be tension minus M1G. A1Y. Okay. Okay, so we have a couple, we have these two masses that are moving. We have the basic sum of forces in the Y direction for each one of them. We're keeping track of our positive and negative directions. So for mass 2, acceleration is negative, whereas mass 1, it's positive. Okay. So let's just start working with, so a couple of things we're going to need is we're going to need what that acceleration is. We're going to need tension. We're going to end up needing to calculate a bunch of this stuff so we can do our sum of forces and see if it equals mass times gravity. Okay, so let's start with our sum of forces for mass 2 in the y direction. And we're going to take account of they both equal acceleration in the y direction. It just depends on which way it's pointing. Okay, so you see that we can go ahead and turn mass 2 times AY. You just multiply through by -1. Now, let's look at the sum of forces for mass 1. G is going to equal M1G 1AY.
Why do they all equal each other? The A2Y, A1Y, AY.
Well, because this is a single system, and when it starts moving, both blocks are going to move at the same acceleration. It's just when you're looking at the free body diagram, you start out saying, well, I have acceleration for mass 1, acceleration for mass 2, but since it's the same cable, you end up at the point where you say, well, they're both just the same acceleration, just in opposite directions. So then we're going to take this, put it in there. G minus G Y. Now from here, if I want to solve for my acceleration, what do you think I need to do now?
M2.
I need all my accelerations on the same side of the equation. No, first we're just going to do now we're going to factor out the AY. This is actually a very classic solution in Newtonian mechanics. Okay, so you go back up to the problem and you look at all the numbers, you can solve. You should get an AY of about 2.31 meters per second squared. If anything, I want you to at least be able to get to this acceleration, since this is one of the most classic solutions in mechanics. And remember, if you're ever looking this up, this is called the Atwood machine.
Can you put the numbers in like the equation so we can see how you do it?
Y, that's going to be 42 kilograms.
Likewise.
Now we have an expression for our acceleration. We're going to work through to another very classic solution, the tension on the cord between the two masses. Remember, we had this equation. Take that and put it in there. Factor out the G. Now, to get to this solution, we're going to end up doing using one of the most common tricks in physics called multiplying by 1. So you notice here that we have on the right side, we have a fraction with a denominator of m2 plus m1. So what we can do, take that m1 there, we're going to make it so we're going to take the denominator from the right side and just put it over itself. That makes it 1. And so what this is going to become m1 m2 m1 squared now we're going to plug that back in for that m1. We're going to end up doing that on both sides. Yep. Let me check my notes here for a second. I hate it when I do something a week ago and then I'm like, why did I do that? Oh, I know what I did. So I'm going to multiply this m1 in here. Okay, and now I have an addition of two fractions with the same denominator. And let's see what ends up disappearing. And 1 squared goes away. And my tension ends up being gravity So that's what the solution for tension is. Now, I did this whole derivation because he put this in the textbook and didn't show you any of the in-between stuff. Did not show you how he got there, so.
So now when we like would use this for our assignment, we don't have to derive from the beginning, right? We can just put tension.
Yeah, if you end up using this, I would go straight for the tension equation. You're not actually going to get problems that are going to be this involved. I just want you to see, since he put the equation in the textbook, I want you to see where it came from. So we can solve for tension now. And your tension should come out to be about 315 newtons. Now, the question is, does this verify, we have all of the forces we need now. Does this verify Newton's second law? Okay, so let's go back, let's look at mass one. So remember some of our forces in Y, we had tension minus mg equals m1 ay. Okay, so tension, 315 newtons, minus m1g, that's going to be 26.0 kilograms. (9.8 meters per second squared) equals 26.0 kilograms. And then A was 2.31 meters per second squared. And when you use your calculator, you get right at 60 newtons equals 60 newtons.
Yes.
Of course, you could do the same thing for M2, and you'll see that that one comes out to be 97 newtons and 97 newtons. So yes, this does verify Newton's second law. And the Atwood machine is one of the most famous experiments for verifying that. We still have some time, so we're going to start talking about the last little bit of this chapter. I was going to skip over this until I saw that it was on the MCAT. And some people are going to have to take the MCAT. Is there a standardized exam for veterinary school? No? Oh, yeah. Relative velocity. Okay, so this is where we start getting into, you see one thing, I see another thing, and then the truth is something completely different. This was kind of where the whole idea of relativity started. I mean, imagine you have a person standing on the ground that's not moving and a person that's on a train car that's moving. Well, for example, see the person on the train car, if they're throwing the ball, they only see it moving in the up and down direction, whereas the person on the ground sees it going like this. So that's one type of relative velocity. If the person on the train starts walking, they can see themselves moving at a certain velocity, but the person on the ground would see them moving at their velocity plus the velocity of the train car. So a good example is, let's say, You have, person A, person B, object A, object B. Person A is moving with a velocity vector at 3 meters per second, going that way. Person B moves a velocity vector of 5 meters per second, going to the right. So if person A looks back at person B, how fast is person B according to person A? 8 meters per second. According to each one of them, they're separating at 8 meters per second. But that's just what they're seeing. The actual truth of the matter is one is moving at 3 and one is moving at 5 because you measure it from a fixed position. So we'll get a little deep. We'll finish off this chapter on Wednesday. We'll finish off with a problem of relative velocity so you can kind of see what that's like. If you don't have to take the MCAT, you can kind of just go, eh. I'm not going to put relative velocity on homework for an exam, but if you have the MCAT, you're going to want to learn this. Yeah, on Thursday, yeah, there's an exam on Thursday. So,
Can you move the homework?
yes. So your exam is going to be everything up to the end of this chapter because, of course, I'm not putting relative velocity on there. Yeah. So yeah, chapters 2 and chapters 3. Kind of. Wait till you see it in 2 dimensions. It could up to like the Atwood Machine, yes. No, that was the one with the two masses and the tension in the rope. Yeah.
Figure it out. So I don't.
Yeah. No, I'm not gonna make.
I didn't know that was homework, so I just looked at it last night.
But I'm gonna make them less intense than you would.
Yeah, I went into
because, again, you have like an hour to do the exam, you have 7 days to do the homework.
So we still have homework to do. Do I need to?
Yes.
Since my app's all
Put
day.
that up at the end,
Because I'm going to fix it. Because it's pissing me off.
So what would you say, like,
Log into like
studying
campus on my